second law of thermodynamics. First one, Kelvin Planck statement. Kelvin Planck statement. It means mainly, see, heat engines, any engines we are designing. Okay. Suppose for an engine, we are giving some input, that be fuel or electricity or whatever it is, and we are taking an output. For example, we are pouring 1 liter petrol, and car is, moving through 50 kilometer, or it is going to 12 kilometer with the petrol, for example. That means that car is doing a work. We are giving a fuel, we are taking a work. But car engine is heated because it has to overcome the friction and machinery parts are working. This is all waste of energy. That means around 60% fuel energy only that car is using for running. All 40% is going in the form of heat wastage. So this is what Kelvin statement, Planck statement, Kelvin Planck statement says. Kelvin Planck statement says no engine is designed so far with 100% efficiency. But here what I have written, statement is little twisted, but this is the meaning of it. In case you did not get this big statement, you can write, until now, no engines are designed with 100% efficiency. That's the meaning of this statement. But in physics, some statements are given little twisted. The actual statement is this. Look here. It is not possible to construct an engine which will produce no effect other than extract the heat from the reservoir. Heat from the reservoir means supplier. Heat from the reservoir and perform an equivalent amount of work. So we expect a machine after designing extract complete amount of energy and convert into work. But we cannot design. That's what. It is not possible to construct an engine which will produce no effects, okay, other than the extraction of heat from the reservoir and perform an equivalent amount of work. This is the first statement. Means 100% efficiency is not possible. It's only work, 100% work is converting. So until now, it cannot design any device. That's the first statement. Second one, Clausius statement. Clausius statement. This is mainly for designing of refrigerators, AC, freezer, these kind of things. That means after purchasing a refrigerator, if you're keeping it home and keep the food, will it cool? No. We have to connect with electricity. That means there is a device called compressor. So this compressor takes in energy inward, extracting some energy, and from lower temperature, it has to take the heat and throw into outer. This time, this refrigerator detailed learning was there, but this time it's removed. So I can only explain this way because it's not in syllabus. So after taking this energy from the from the electric supply, this device will throw that energy from low temperature to high temperature. Always temperature goes from high temperature to low temperature only, heat. A refrigerator just keeping, automatically heat will flow out to in. That's what in our house we feel warm. But what is the work of AC? Taking from inner to out. So outer may be 50 degrees Celsius, but inner AC will maintain 15 degree or 20 degree what you set. That means this AC should keep on taking the heat energy from lower temperature to higher temperature. For that, an external agency is required. Just if you're purchasing an AC and keeping in your room, that cannot take the heat from lower temperature to higher temperature, because it will always flow from high to lower. That's your second statement. It is impossible for a self-acting machine. It is impossible for a self-acting machine unaided by an external agency, without an external agency, means compressor, to transfer heat energy from a body at low temperature to another body at high temperature. This is applicable for refrigerator. This is second law. Okay, these two laws. So second law they're asking, there are two laws, Kelvin Planck statement and Clausius statement. Kelvin Planck statement helps us to design heat engines. So don't think of 100% efficiency. Even in future also, you can never get 100% efficiency. Okay, because in ideal condition, it is proved, because there is no 100% efficiency possible. Then Clausius statement talking about how to design these kind of machines that can take heat from lower temperature to higher temperature. That means refrigerator, AC, these kind of things. That means without compressor, we cannot take the heat from lower temperature to higher temperature. There is no self-acting machine without an external agency. It can take the heat from low temperature to high temperature. Okay. Next one, reversible and irreversible process. See, for example, Hooke's law, we studied Hooke's law, right? When we are adding the load until elastic limit, it's increasing. When we are unloading, that's coming back to initial position. So there, very slow loading does not lose any energy. This kind of process we can call reversible process. That means if you plot a PV diagram, see, this is a PV diagram, pressure volume, this one. A gas which we are slowly expanding, for example. Okay, this is onward process. Now, if we can bring it along the same way without wasting energy, okay, that means A to B expansion, B to A contraction. It should happen along the same path. If it is possible, this is reversible process. In reversible process, I told you area under this graph. For example, dV is a small portion. This is P. So dW is equal to PdV. Pressure into this area under the graph will give you PdV. And total area under the graph will give you total work done. That is integration of PdV, V1 to V2, we told you. That means on A to B, if you're calculating area, B to A, you're getting same area, but minus. Then total work done will be zero. Question can be asked. In a what is reversible process? Reversible process is the process in which every state of onward process can be retraced in the reverse process. So that total work done will be zero. There is no net work done. There is no energy wastage. It's just like a conservative field. This is the reversible process. Now there is cyclic process. Cyclic process means, look here, what is the cyclic process? In cyclic process, see, first it goes to A to B and B to C, then C to D, and it come back to D to A. So it came back to its initial state. If it come back to its initial state, means its internal energy remains same. That same state it came back, but not along the same path. Here you can see area under this graph if you are taking. See, area under AB is more than area under CD. Then if you subtract, you will get area of this region. You will get area of this region. Now there is a work done. This is happening in a reversible, cyclic process. Cyclic process means, example, car engine. We can take an example, cyclic process. Okay, in a car engine, first let me come to a cyclic process with another example. There is an engine designed which is called Carnot engine. All engines are the modified form of this. This is designed in ideal condition. It is called Carnot engine. How it works, first it's a theoretical explanation. After studying this, we'll go to real examples. Okay, what is a Carnot engine? This will explain about cyclic process very clearly. Look here. Here there is a source. There is a source. This is at a temperature T1. For example, fuel, petrol, whatever it is you're keeping here, that's a source. It is at a temperature T1. Think it has a 100%, infinite heat capacity. What is the infinite heat capacity? Heat capacity is the amount of heat required to raise 1 kilogram of body to 1 degree Celsius. Infinite heat capacity means how much amount of heat if you're giving, the temperature will not rise to 1 degree. That's called infinite heat capacity. Or only after giving infinite amount of heat to the system, temperature should rise to 1 degree. That's called infinite heat capacity. That means ideally we have to bring and keep sun here, for example. So its ideal conditions are only imaginary. We cannot do it. Okay, next one. Same way, infinite heat capacity. If you're taking away heat also, the temperature should not change. That is source. This is a property of source here in ideal condition. Next one. This is designed by Carnot. Okay. Next one here, there is a cylinder. This cylinder with all perfectly conducting surface, perfectly conducting walls. And this is frictionless piston. This is insulating wall, down perfectly conducting base, side perfectly insulated. We don't get we never get perfect insulator or perfect conductor. But we are assuming this is perfect insulator, down perfect conductor. And this is a piston. It can move frictionless. So there also heat loss is not there. This is a stand, okay, insulating pad. This is called insulating pad. Here we have taken ideal gas. Everything ideal. Insulating pad means 100% insulator. And here there is sink. This is called sink. Sink means heat rejecting into that. For example, in a car, radiator has water in it. So after driving the car, if there is no water in the radiator, your car engine will be heated. So usually that heat rejecting by the engine is absorbed by water. Still, it is very hot. You know that. So here we have to use sink at a temperature T2. This should have a lower temperature and infinite heat capacity. Ideally, how much amount of heat you are supplying, temperature should not rise. This is the ideal conditions. Now we are plotting a graph on this. Okay, so these graphs are important. To explain this graph, we need the system to understand. First, I'm keeping this ideal gas above this, okay? Like this, I'm keeping here, above this. Now here, ideal gas is there. Heat slowly supply into it, slowly supply the heat so that temperature should not increase. That means there should not be friction, it should expand. Isn't it? That system should expand slowly. That means how much heat you are giving. Suppose if an amount of heat is going here, immediately internal energy of the system will increase. Provided this we are holding. We are not allowing to volume expanding. So the energy are supplying immediately using for increase in kinetic energy of the molecule. That means increase in internal energy. But as soon as this heat entering, if you are expanding, that energy will be used for what purpose? Expansion. Because dq is equal to du plus dw. dw means pdv. If du is constant, dq is equal to dw. Here that's happening. The moment heat is supplied to here, this will expand. dv will produce. So that this heat directly using for expansion. So du remains constant, therefore temperature remains constant. So this kind of expansion is known as isothermal. Iso means same, thermal means temperature. So this type of expansion is known as isothermal expansion. So usually isothermal expansion is marked like this. This I'm marking A to B. Okay, isothermal expansion. Area under the graph will give you work done for this isothermal expansion. Now suddenly this we are transferring onto the insulating pad. Now no heat supply. Okay, then again expansion is going on. For expansion, it requires energy. So it has to use its own energy. So now internal energy will decrease because dq is 0. For example, see, I am telling you to do some work. So you have 100 reals in your pocket. I said, okay, keep there. I will give you 10 real. Finish that work. Okay, I'm giving 10 real. With that 10 real, you're doing work. Again, I'm giving 10 real. You're doing work. Again, I'm giving 10 real. You're doing work. This process continuing. This is isothermal. That means your internal energy, what you have in your pocket, is not affected. The money I'm giving directly you're using for a work. Suddenly I stop giving. So you think, just like inertia, you think I will supply, you take from your pocket and spend. Now your energy become 90. I'm not giving now. Supply stopped. So from each time, from your pocket, you will supply. This is called adiabatic expansion. Heat supply stopped. Therefore, that working substance or gas uses its own energy and temperature decreases. So here we can say P1, V1, T1 temperature. Here it is P2, V2, temperature remains same. But here you can see temperature suddenly decreases in this process. This is called adiabatic expansion. In adiabatic expansion, dq is equal to 0. Okay, in that case, you see when dq is equal to 0, look at what happened. When dq is equal to du plus pdv. When dq is equal to 0, okay, du is equal to minus pdv. That means when there is an expansion, there's a decrease in energy. Okay. When there is expansion, there is a decrease in energy produced. Is it clear? That's what minus sign indicates. Sometimes they will ask, prove that in adiabatic expansion, energy is negative, energy is decreasing. So this way you have to prove. By first law of thermodynamics, dq is equal to du plus pdv. In adiabatic expansion, dq 0. Therefore, if dv positive, that means dv increasing. dv means change in volume. Then du must be negative. Is it clear? This is the meaning of it. Now, next again, what we do, this one you are supplying over this sink. Okay, then what happened? This is lower temperature. This time it start rejecting heat into sink. So its volume decreasing now. This is decreasing. Okay, this is isothermal compression. That means if you're pressing it, slowly you have to press it after keeping over here. So the work you're giving directly rejecting into sink. If it is not rejecting, if it is blocked, what happened? You are doing work. That work will act as a increasing energy. So system will develop an increase in energy. If you want to do one thing, take a bottle and shake it. After some time, you can see that water will be hot. Because you are doing a work. Similarly, if you keep this system on this sink and compress it slowly, so your work will convert into energy, increase in energy. But that energy should immediately transfer to the sink. Then temperature remains constant. This is called isothermal compression. So here P2, V2, T2. See T1 become T2. Here again P3, V3, T2. Isothermal compression. That means compression at which temperature remains constant. Again, we are keeping it back. Quickly are compressing. See, it will come back to its initial state. Now, clear? Now, total energy, temperature again same. So how it started with the temperature, same temperature it came back, but passing through different cycles. Clear? That means in a car engine, after receiving the fuel burned, that piston, you know the piston, right? In car engine has a piston like this. See, this is the crankshaft here. Okay, this is connected to a piston like this in car engine. That means this square one like this. Okay, here there is one square piece like this. Here a piston. So when square piece is moving forward, piston will be pushed inward. That square piece come back, piston will be pulled back. So while this is rotating, piston move to and fro. So this is a system, rotational motion we can convert into linear motion. So here first it compress, then it come back to initial state. So here also during one compression, come back, this is the graph you are getting. So area, this work, right, this region, if you calculate, that is a work done, useful work done. All other part is lost in the form of energy. So this is a cyclic process. So here mainly we understand isothermal process, adiabatic process, isothermal expansion, the expansion in which temperature remains constant. Adiabatic expansion, the expansion in which heat supply dq 0, temperature decreases. Isothermal compression, compression in which temperature doesn't change. And this is adiabatic compression. That means temperature increases. Suppose when you are blowing, inflate a balloon and suddenly you release and keep your hand here, you feel very cold. The reason is adiabatic expansion. Suddenly it's expanding. Air is the insulator. So what happened? No heat will be supplying from air. Then that gas uses its own energy to expand. So it becomes cool. That is cool. Sometimes in jet planes while traveling through the air, you can see thick fog behind it. Because that hot gases, when they come out, suddenly it expands. In that expansion, surroundings, air will be cooled. So humidity will become condensed water. That's what thick water only are seeing like a fog behind some jet plane, two trails you can see. So these are all examples for this one. Okay. And this cycle is known as Carnot cycle actually. Based on this, he designed some engines and all. Now you don't have to study that actually. You have to study what is isothermal process, adiabatic process, cyclic process. This only mainly you have to study them. Is it clear? Right. Now next heat engine is there, refrigerator is there. You don't have to study, cancelled it. Okay. If it's in the note, just strike it. You don't have to study that. Next, we have to study kinetic theory of gases. Okay, kinetic theory. There are around 8 postulates in kinetic theory. So first postulate, a gas consists of large number of molecules which are perfectly elastic spheres. and are identical in all aspects. For example, hydrogen, if you are taking, all hydrogen molecules are same. Oxygen, if you are taking, all oxygen molecules are same. But a hydrogen molecule does not resemble an oxygen molecule. Size is different. That's the thing. Okay. Second one, the
Sir,
molecule. What? Tell me. Ask. Ask.
sir, so you are we will never write the notes, sir, in the notebook, sir, or
Note
we
and
will always get, you'll always send us the PDF.
that you follow now. That notes.
Sir, but if we write, we will have more practice. Like it
No
will be
time. That is
better,
the
sir.
problem. I'm telling you. I know that you have more practice. But school asked us to finish the portion by this month. By writing note, can we finish it?
No, sir.
Sir,
That's what I'm saying. For the time being, you do one thing, you follow this note, you take printout of this note and just read it and come. That's what I told you. Only this chapter,
okay,
all the time when we had time, I went very detailed. I gave the note. We solved all numericals. But this time, and you won't come for extra class, you won't come for vacation class. Immediately you will go with a complaint to the principal. Then how will I finish the portion? And
yes,
this is
sir.
the technical in higher classes we have to finish, no other way. So now you do one thing. This
Yes, sir.
also you finish this note, PDF notes. Next chapter onward, that's a new thing. Because it's very difficult to understand. This you studied at least in chemistry. First, let me finish that. Oscillation and
Yes, sir.
waves. That I will give the note, but Friday, Saturday, compulsory have to come. Otherwise, again, I will go for this work. Then December, January, I will come back to
Okay.
this portion, which I went fast. Then I will go slowly. So I'm peaceful because the school will not compel us. Parents cannot complain because only those who are interested join. That's all. I cannot compel anyone. The problem mainly everything you are complaining. You are not thinking about our effort, what we are doing for you. If you're studying little more, parents are so soft. Immediately they go and complain. What can we do? We have to finish the portion, like this much portion, 1 year, this much time we are getting. How can I finish? You think in between so much disturbance. Okay, this is now you cooperate. I can't do anything. I am also very sad of finishing like this because I also lost interest of teaching. Now, concept of pressure exerted by the gas. Next chapter onwards, I'll give the note. Now you cooperate with this. Pressure, concept of pressure exerted by the gas. Okay, look here. I told you the pressure in solids because of its weight. Pressure in liquid also related to its weight and collision. Pressure in gas just because of collision, their weight factor is neglected. That means 1 second, how many times it collide on the walls, that decides pressure of the gas. So there is a formula derived. You don't need derivation, just you have to by heart the formula. Okay. Pressure exerted by the gas in a container is equal to 1 by 3 rho c squared. Rho means density of the gas. C is root means square velocity. So this C we can write as root of C1 square plus C2 square plus Cn square and divided by n. This is root means square velocity we call. Okay. Now, from here, C bar, root means square velocity if you want to calculate, you have to do it. C squared is equal to 3p by rho and C is equal to root of 3p by rho. That means if you know the pressure and density, we can calculate root means square velocity. Otherwise, like definition, every molecule you cannot calculate. See, one molecule may be going with 4 kilometer per second. Other molecule may be going with 8 kilometer per second. Other may be going with 3 kilometer per second. How can you calculate individually? So this is the definition. But while calculating pressure and density, root, this formula, you can calculate this one. Root mean square velocity. Okay, this is the RMS velocity we can say. Now, relation between pressure and kinetic energy. Okay, look here. P is equal to 1 by 3 rho c squared. Okay, then kinetic energy is equal to half mc squared. Okay, so here kinetic energy per unit volume, then half mc squared divided by v. M by v is rho c squared. Okay, So this is P is equal to 1 by 3 rho c squared. This is 1 by 2 rho c squared. Now we are dividing. So kinetic energy, pressure divided by kinetic energy per unit volume, if you're taking 1 by 3 rho c squared divided by 1 by 2 rho c squared. This is cancelled. Then P divided by kinetic energy per unit volume is equal to 2 by 3. That means P is equal to kinetic energy is equal to 3 by 2 of pressure. Clear? So if you know the pressure, 3 by 2 take, that will be the average kinetic energy of that gas. Okay. Now, next one, average kinetic energy per molecule of a gas. Okay. So here, consider 1 mole of a gas at a temperature T and the volume V. M is the molecular weight and N is Avogadro number. What is the meaning of Avogadro number? Avogadro number means number of molecules present in 1 mole of gas. For water, 18 gram is its molecular weight. That will contain 6.023 into 10 to the power 23 molecules. It will be there in that 1 mole. Okay, that is Avogadro number. So based on this, we are writing, look here, mass of 1 mole of gas. There are n molecule in 1 mole of gas. That is Avogadro number. Mass of 1 molecule is m. So n into m is the mass of 1 mole of the gas. And this is equal to molecular weight, we can say. And kinetic pressure exerted by the gas, we know P is equal to 1 by 3 rho c squared. Then here P is equal to 1 by 3 rho is m by v c squared. Okay. Then here by general gas equation, PV is equal to RT. And P is equal to, here PV is equal to RT, right? So P is equal to RT by V. 1 minute. P is equal to 1 by 3 MC squared, this R. Now we equate these two. RT is equal to PV is equal to RT, right? PV is equal to RT. So this V I am taking here. V is equal to 1 by 3 MC squared. PV is equal to RT, we are substituting. So RT is equal to 1 by 3 MC squared. Okay. Then here, now we can calculate both sides multiply by 3 by 2. Then 3 by 2 RT is equal to 3 by 2 into 1 by 3. 3 by 2 into 1 by 3 MC squared. 3 cancel. 3 by 2 RT is equal to half MC squared. Okay, so this is average 1 mole of the gas.
Sir, how 3 by 2?
Both sides multiplying by 3 by 2. So that right side we get half. So we get kinetic energy half MC squared. Clear? We are multiplying both sides. So equation doesn't change because we need kinetic energy formula. That's why. So this is half and MC squared is nothing but kinetic energy per 1 mole. That's equal to 3 by 2 RT. Okay. Now it shows that kinetic energy per 1 mole is directly proportional to temperature. This is what I told you from the beginning. Kinetic energy of the gas molecule is directly proportional to temperature. Now here, this kinetic energy, right? M here, this M, you give M into N. Then you will get kinetic energy per 1 molecule of the gas from that. So from there you can get, where everywhere you can prove kinetic energy, average kinetic energy of 1 mole of gas or